Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
Scott Aaronson is the David J. Bruton Centennial Professor of Computer Science at the University of Texas at Austin and director of its Quantum Information Center. Previously, he spent 9 years as a professor in the Electrical Engineering and Computer Science Department at MIT. Scott's primary area of research is quantum computing and computational complexity theory more generally. He holds a bachelor's degree from Cornell University, a PhD in computer science from the University of California, Berkeley, and did postdoctoral fellowships at the Institute for Advanced Study, as well as the University of Waterloo. He writes a popular blog and is also the author of Quantum Computing Since Democritus. Scott, welcome to Data Skeptic.
Thanks. Great to be here.
So we're going to talk about quantum computing today. To set the stage, maybe can you describe the difference between a classical computer and a quantum computer?
Well, a classical computer operates on bits, which are in a 0 state or a 1 state. A quantum computer operates on a more general kind of object called quantum bits or qubits, which can be in what we call a superposition of the 0 and 1 states. It's hard to explain it in a sentence or two without having to say, what is quantum mechanics, and how did physics change about 90 years ago? Basically, what quantum mechanics says is that to every possible configuration that an object could be in, whether it's an electron or even a computer, we have to assign a number called an amplitude. Amplitudes are a little bit like probabilities, how likely it is that you'll find something in one state or another. In fact, we use amplitudes to calculate the probabilities that we'll see a computer in one state or another if we measure it. But amplitudes are not probabilities, okay? And the key difference is that they can be positive or negative, or in fact, even complex numbers. Okay, so we'd never talk about a negative 30% chance of rain. That would just be nonsense. But in quantum mechanics, everything is based on these complex numbers, these amplitudes. So what a quantum computer would do basically is sort of choreograph an enormous wave of these amplitudes. Okay, and the key thing that amplitudes can do that conventional probabilities cannot do is that they can, as we say, interfere with each other. So like if some outcome could happen in one way with a positive amplitude and in another way with a negative amplitude, then those two contributions can interfere destructively and cancel each other out, meaning that outcome would never happen at all. This famously happens in the double slit experiment, where you shoot photons one at a time at a screen with two slits in it. What you find is that on a second screen, there are certain spots where the photon never appears. And yet, if I closed off one of the slits, then the photon could appear in those spots. So by decreasing the number of ways for something to happen, I can increase the chance that it happens. Okay, and this is only explainable, in terms of these amplitudes. So we're saying the photon has some amplitude to reach the spot going through the first slit, some other amplitude to reach the spot going through the second slit. If both slits are open, then these two amplitudes, if one is positive and the other is negative, they can interfere destructively and cancel each other out, meaning that the photon is never seen there at all. Whereas if I close off one of the slits, then the amplitude is only positive or it's only negative, meaning that the photon can appear there. Okay, so in a sentence, a quantum computer is just a computer that would exploit this phenomenon of interference of amplitudes on a massive scale. Okay, so it's not just like the computers that we have today, but faster. It's a fundamentally different way of harnessing nature to do computation. It helps you sort of if and only if you can figure out how to exploit this pattern of interference. The idea with any quantum computation is that we try to choreograph things so that for each wrong answer, some paths leading there have positive amplitude, others have negative amplitude. So on the whole, they cancel each other out. Whereas for the right answer, we want all the paths leading there to reinforce each other. Okay, and this is happening with an immense number of amplitudes, right? Because if I have a quantum computer with, let's say, 1,000 quantum bits, or 1,000 qubits, The rules of quantum mechanics say that to fully describe that computer, I need 2 to the 1,000 power amplitudes. That's one for every possible configuration of all 1,000 of the qubits. So that's actually a much, much greater number of complex numbers, than I could even write down in the whole visible universe. Quantum mechanics has told us since the 1920s that nature has this unbelievable amount of stuff going on under the hood, this huge sort of potential computational power. Okay, the trouble is when you measure a quantum system, you only see one outcome. The rule is that the probability that you see a particular outcome is given by the squared absolute value of its amplitude. So you measure and you just see one thing. But if you were able to cleverly choreograph a pattern of interference, then you can boost the probability of seeing something that you want, like, the answer to your computational problem, as opposed to all of this, enormous exponential number of things that you didn't want to see. So that's the basic idea of a quantum computer.
I'm appreciative you didn't use this phrase, but a lot of people who talk about quantum somehow throw the term parallel universes around a lot.
Yes.
So it's very appealing almost in a way to think, well, if I can exploit parallel universes, that sounds a little bit like an NP problem. If in each universe I make one guess and one of those solutions works out, well, I can solve NP problems in P time on a quantum computer. Why am I wrong?
Right. Right. What you're describing is how pretty much every popular article that's ever been written on this subject for the last 20 years has described it, and all of them are wrong. So some people do like to talk about quantum superpositions, these waves of different amplitudes for each possible outcome, in terms of there literally being different parallel universes. This derives from a famous, interpretation of quantum mechanics called the many worlds interpretation due to Hugh Everett from the 1950s. And that is something that some people believe. But whether you believe in parallel universes or not, first of all, it's up to you. That's a matter of interpretation or a matter of philosophy. But secondly, regardless of whether you believe it, this trying each answer in a different parallel universe, it's still a wrong explanation for how a quantum computer works or why it's able to give you the speed up. Here's what's wrong with it. You can, with a quantum computer, very easily, create a superposition over all the possible answers to your problem, even if it's an NP-complete problem, let's say. That's actually a very easy thing to do with a quantum computer. Now, the problem is that, at some point, you've got to measure the thing if you want to get an answer out, if this is to be a useful computer. If I just made an equal superposition over all the possible answers and I measured it, not having done anything else, then the rules of quantum mechanics say that all I'm going to get out will be a random answer. Okay, and of course, if I just wanted a random answer, well, I could have picked one myself with a lot less trouble. The entire hope for getting a speed advantage from a quantum computer is to exploit interference. That, you have to get the paths corresponding to the wrong answers to interfere destructively and cancel each other out. And, you need to do something to boost the amplitude of the right answer. So that's a very subtle effect, and it's only for a few very special problems, as we'll discuss, that we actually know how to exploit that kind of effect to get an exponential speed up over any known classical algorithm. Well, one thing that we don't believe is that even a quantum computer would be able to solve NP-complete problems in polynomial time, for example, okay? Because for NP-complete problems, we don't know how to choreograph this interference effect to actually get the amplitude on the branch that happened to hit the right answer, right? It's we don't want just that some parallel universe gets the right answer. We want you to get the right answer, right? And that's a much harder thing to arrange.
We're in an era when I don't want to say there aren't quantum computers. That would be wrong. I guess we have to be specific with what we mean, but certainly the ones that exist are small scale, not incredibly useful for doing any types of real world problem solving just yet.
No, not useful at all yet, I don't think.
So maybe there's a question then too of will we ever have a useful one?
Yes.
In Quantum Computing Since Democritus, you outlined 11 objections. I'm going to ask users to go to the book to hear all of them, but there were a couple I wanted to cover here. The first one being that it works on paper but not in practice. Why would I think that might be a reason we couldn't get a quantum computer?
Since the very beginning of this field, there have been people who have said, maybe the equations of quantum mechanics suggest that you could do this, but you're never going to do it in reality. You can go back to almost any technology, classical computers. People said that to Charles Babbage, right? Or, heavier than air flying machines. Maybe birds do it, so it's possible in theory, but you're never going to do it in reality. And a lot of these things, it just comes down to, well, how badly do people want to do it in reality, right? Like, things work on paper and not in practice, until someone invests enough effort, and then they do work in practice. There was a sort of a deeper objection. It has to do with sort of what we've known since the beginning is the central technological problem with actually building a useful quantum computer. Okay, and this is something called decoherence. So decoherence basically means unwanted interaction between a quantum computer and its external environment. The trouble with that sort of interaction is that, it can have the effect of prematurely measuring the computer's state. Okay, so, I said before that, as soon as you look at a quantum state, these amplitudes turn into probabilities, which is just another way of saying that the superposition collapses to a single definite outcome. This is the famous collapse of the wave function. But, and this confuses many people because, it sounds like human consciousness is playing some central role in physics. But in fact, there's nothing that says that it has to be a conscious being looking at a quantum state to change it in this way. In fact, any interaction with the environment, whether that means a recording device or even just some stray particles in the room, if it carries information away about whether your qubit was in a 0 state or a 1 state, then that will have the same effect, as if your qubit was measured. Okay, namely, it will collapse the qubit's quantum state, and force it back down to being a classical state. So the bottom line is that this superposition and interference is something that qubits like to indulge in private. Okay, they don't like to do it when anyone is watching them. The only reason why, this is the reason in some sense why we don't notice quantum interference effects on the scale of everyday life. It's the reason why people had to go down to the atomic scale in the early 20th century before they discovered that the world really does work this way. The hard part of building a quantum computer is that, you have to have a collection of, say, thousands or even millions of qubits if you're trying to do something useful. You have to keep these qubits sort of fanatically well isolated from their external environment in order to maintain their quantum state, which is this very fragile thing. But then at the same time, the qubits have to be interacting with each other, but in a very precisely choreographed way in order to do the computation that you want. In the 90s, there were some physicists who said, well, that can never work. Right? You are just never going to get qubits well enough isolated from their environment that you could actually do a whole computation with them. Okay, maybe it's just, an empirical question, right? Maybe you can and maybe you can't. But there was one really big discovery in the 90s that changed almost everyone's opinions about this and established in most people's minds that, okay, this is merely, quote unquote, a staggeringly hard engineering problem. There's no problem of fundamental physics here. Okay, and that discovery was what we call quantum error correction and more generally quantum fault tolerance. What quantum fault tolerance said is that you don't actually have to get the rate of decoherence down to 0 in order to build a useful quantum computer. It is enough to get the decoherence rate down to some very small but non-zero level. Okay, so even if each of your qubits is coupled to its environment, is interacting with its environment, or let's say has some chance of decohering, at every step of the computation, as long as it's a slow enough rate, you can encode quantum information that you care about non-locally across many different qubits using very, very clever quantum generalizations of error correcting codes in such a way that even if, let's say, any 1% of your qubits were to leak out or, decohere, be lost to the environment, you can still recover information that you care about from the remaining qubits. So, you would have to be constantly pumping noisy qubits out of your system, pumping fresh qubits into it, constantly measuring to see, so this is the tricky part, measuring your computer to see if an error has occurred, and if so, how do you fix it, but not measuring anything else about the computer. Okay. Not measuring, the quantum state that you don't want to measure, but just measuring to see if an error has happened, doing this in parallel across all of the qubits. And if you can arrange all of that, then even with noisy qubits, the theorem said that you could do an arbitrarily long quantum computation. Okay, so since then, the main goal of the engineers in this field, the main experimental goal, has just been to get systems that have low enough decoherence, or where the hardware is good enough that you can start bootstrapping, start using these error correcting codes in order to simulate qubits that would be even better and better. And, once you've sort of crossed that threshold, then just like with a classical computer, you'll only be limited by how big of a system do you want to build. So, we're not yet at that point, but the exciting thing right now is that, just within the last few years, people have finally gotten qubits where, at least when you look at just one or two of them in isolation, they're already good enough to do this fault tolerance stuff. When you integrate a large number of them, they're all going to have unwanted interactions with each other, and that's going to push the decoherence back up. But at least we have qubits that are now sort of good enough in isolation. And that's why it finally makes sense for people to start building systems that integrate, let's say, about 50 of them, which is exactly what is happening this year.
Yeah, it's exciting. I myself have kind of started to compare it to like having a civilization on Mars. We're not going to have one tomorrow, and there's a lot of open challenges and questions to be figured out, but there's no impossibility theorem saying we can't do that. Is that a fair analogy?
I mean, I think so. The way I would put it is that if there is some deep reason why you cannot build a quantum computer, then that's actually way more exciting than if you can build one, because, that says that we have to rewrite the physics books. At this point, if you believe the basic principles of quantum mechanics and, and the way that physicists have applied them for a century, then it is very, very hard to understand why a quantum computer could not be built. If there's some deep reason why not, then that itself would be a revolution in physics. By the way, I personally am optimistic that we will get useful quantum computers before we get a colony on Mars.
Oh, well, yeah. With that in mind, what do you think realistic timeframes are? Like, well, I know there are some commercial offerings, but when will we get a quote-unquote useful quantum computer? Are you considering an advanced degree? How would a Master of Science in Business Analytics advance your career? The Mendoza College of Business at the University of Notre Dame has a program that can be completed in as quickly as 12 months. Downtown Chicago classes take place on Fridays and Saturdays. This program will teach you to make strategic business decisions based on data, not on anecdotes. To data skeptic listeners, that might sound like an obvious statement, but let me tell you, the business world isn't always as data-driven as it should be. That's why we need more data-driven professionals. Find out if the Masters of Science in Business Analytics could help you be one of those thought leaders. Visit mendoza.nd.edu/dataskeptic or email msba.business@nd.edu. There are some commercial offerings, but when will we get a quote-unquote useful quantum computer?
So it depends a lot on useful for what.
Right.
In terms of a computer that just proves the point that, it can do something faster than a classical computer. I don't say something useful, something commercially valuable, just something that will prove the skeptics wrong, and show that, yes, it is possible to get a speed up this way. People are currently racing to do that, and they may do that within this year. That's the kind of time frame we're talking about. Google and IBM right now have 50 qubit chips, that they're still working on calibrating and, getting the qubits to work well. But within the coming year, both of them and possibly others are going to be doing experiments that involve, using these 50 qubits to sample from some probability distribution over 50-bit strings where, we think that to do that with a classical computer would take something like 2 to the 50th steps. So it's like with a classical computer, yes, you can do it. And in fact, you'll have to do it in order to verify the output of the quantum computer. Okay. But if our current beliefs and computational complexity are anywhere close to correct, then, it ought to take a vastly longer amount of time. That will be a major milestone. And I think, if and when it's achieved, it'll put us in a much better position to then think about, okay, now how do we do something useful with this? In terms of useful quantum computers, I'm almost certain that the first kind that we're going to see will be special purpose devices that are mainly useful just for simulating quantum mechanics itself. That was actually the original application of quantum computers that Richard Feynman thought of when he first proposed the idea of quantum computers, along with a few other people in the early 1980s. Chemists and physicists have known for decades that, if you're trying to simulate a chemical reaction with your classical computer, and you need to get the whole wave function, the time needed to do that can grow exponentially with the number of particles, because that's how many amplitudes we're dealing with. So that's been a practical problem for a long time, simulating quantum mechanics with a conventional computer. And you could say, the original goal of quantum computers was to turn that lemon into lemonade, build computers that themselves would be based on quantum mechanical principles and that therefore would be able to simulate quantum systems much faster. That's the first application that I think we're likely to see. There have been studies saying that even if you only have, say, a few hundred error-corrected qubits, that is already enough to start learning new things about, say, chemical reactions, including ones that could be important to industry, like the Haber process, which is how most of the world's fertilizer gets produced. Also, maybe learning about drugs and how they bind to receptors, doing biochemistry, maybe trying to learn how high temperature superconductivity works, building more efficient solar cells. Okay, these are all applications that, you could imagine for, sort of the first generation of useful quantum computers, and I don't know when that's going to come, but there are many companies that are sort of working toward this and that are hoping to start doing something useful, within a 5 to 10 year type of time frame. Only after that will people start working toward the sort of ultimate goal in this field, which is a full, universal, programmable quantum computer, one that is able to do any quantum computation in the same way that our classical computers can do any classical computation. So one that is a quantum Turing machine, if you like, right? And which would be arbitrarily scalable, that could operate on as many qubits as you like. So now, it's only at that final stage that we're likely to build quantum computers that could do sort of, maybe the most famous application of quantum computers, something that we haven't talked about yet, but that is to break public key cryptography.
Mm-hmm.
That is maybe the most notorious thing that you could do with a full quantum computer. You could break RSA encryption, you could break Diffie-Hellman, you could break elliptic curve cryptography. Okay, and so there, you could break almost all of the public key cryptography that people currently use to secure the internet. I don't know that that's a useful application for humanity, but that's certainly a big application for anyone who gets it first, especially if no one else knows that they have it. And so, and that will probably eventually force the world to switch to other forms of encryption. So it will be a solvable problem, but, we will have to adapt our encryption to deal with that. But that's probably only happens sort of once we get the full universal quantum computers.
So we recently covered on the show the P versus NP conjecture, and if listeners took away one thing, I would hope that they know that it's an open problem. We don't have the answer.
That's right.
But it does really seem like P does not equal NP. But we have to leave room for the possibility. In the same respect, do we have any certainties here? Can we say that quantum computers are definitely better than analog computers? It seems that way, but do we know certainly?
Okay, so that's an excellent question. So, by the way, if I like to say that if we were physicists, we would have long ago just declared P not equal to NP to be a law of nature, right? And we would have given ourselves Nobel prizes for the discovery of the law, And if someone else just later proved that P equals NP, well, then we would just give ourselves more Nobel prizes for the law's overthrow. Okay, but because we're math and computer science people, well, we have to call P not equal to NP a conjecture, or an unsolved problem, right? So, so like something, we believe it enough that, we base all of our encryption on that belief, right? And, they're like, well, of course you're going to need brute force search, at least some of the time. How could you not? Okay, but even that is an unsolved problem. When quantum computing came along, one of the main things that we had to do in this field is sort of fit quantum computing into this theory of computational complexity, and the P versus NP problem. This is actually like my stomping grounds, right? This is the kind of stuff that I did as a grad student, is just understand how does quantum mechanics change the basics of complexity theory. A very short summary is that, we can, in fact, my advisor at Berkeley, Umesh Vazirani, and his student, Ethan Bernstein, in the early 90s, they defined a quantum generalization of the class P. They called it BQP, or bounded error quantum polynomial time. Okay, and you can then ask, how does BQP fit in with P and NP, for example? Okay, so at the very least, BQP contains P. Right. So anything you can do with a classical computer, you could also simulate with a quantum computer. So, it's like, if you have a space shuttle, you can also use it to drive down a driveway. We have strong evidence that BQP seems to be larger than P. In particular, I mentioned that quantum computers are known to be able to break almost all of our existing public key cryptography. This is a consequence of the fact that quantum computers can factor integers in polynomial time. That was the famous discovery of Peter Shor 23 years ago, that the factoring problem is in BQP. So that's some evidence that BQP maybe is larger than P, right? At the least, it means that if BQP equals P, then factoring would have to also be in P. But the truth is that we don't have any proof that BQP is larger than P, just like we don't have any proof that NP is larger than P. And in fact, there's this class called P-space, what you could do with a classical computer with a polynomial amount of memory, which is like a ceiling for both NP and BQP. Okay, and no one has even proven that P is different from P-space. And that's considered to be essentially as hard as the P versus NP problem itself. If P were equal to P-space, which again, no one can formally rule out today, then everything would come crashing down. P would equal NP, and P would also equal BQP. Okay, so in such a world, you would already have superpowers, like with no quantum computer, and a quantum computer would give you no additional advantage. Okay, now, we don't think that that's the world that we're living in, but, but none of this is unconditionally proven. The other questions you could ask here is, well, is NP contained in BQP? As I mentioned before, we don't currently believe so, right? Which is equivalent to saying, we don't think that even a quantum computer would be able to solve NP complete problems in polynomial time. Okay, again, that hasn't been proven. I mean, in some sense, there's no hope of proving that yet because we can't even prove that P is not equal to NP, let alone that NP is not in BQP. Okay, so that's again just something we have to assume or conjecture. You could ask, is BQP contained in NP? So, are there problems that a quantum computer could solve, but for which a classical computer cannot even verify the answer? Right, and that we don't really know. We do have candidates for those sorts of problems. There are other settings where we can prove that quantum computers actually get an advantage. One of the most important settings where we can prove an advantage is a setting that's called query complexity. Okay, query complexity means you look only at the number of accesses that your algorithm has to make to the input bits. You ignore everything else. So, we imagine problems where you have a large amount of data stored in some memory, and a quantum computer could access this memory in superposition. So it's classical data, but the quantum computer could, say, go into a superposition of, querying the first bit, querying the second bit, and so forth, and get a superposition of answers with which it could then try to set up an interference pattern. In those sorts of cases, there are problems where a quantum computer is known to be able to solve them using only like a logarithmic number of accesses to the memory, whereas it is proven that any classical algorithm needs a much, much larger number of accesses, something like square root of n, if there are n bits in the memory. An example of such a problem would be if your data encoded a periodic function, a sequence that repeats with some period, and your goal is to find the period. So then you can prove that, well, a classical computer, for it to solve that, it has to look at a large fraction of the whole sequence. Whereas a quantum computer could do this sort of almost immediately by just querying everything in the memory in superposition. And in fact, here's something interesting. This ability of a quantum computer to find the periods of periodic functions is actually the core of how Shor solved the factoring problem in polynomial time with a quantum computer. Mm-hmm. For factoring, the speed up is only conjectural, because for all we know, there could be some completely different way to factor numbers with a classical computer that would be just as good as a quantum computer, right? No one can rule that out. But if we're just talking about accessing this periodic sequence and seeing what its period is, and I tell you that this sequence is stored in a memory and you have no other access to it except by, just making reads to these bits in your memory, then in that kind of situation, you can actually prove that quantum computers do give you an exponential advantage.
So a great deal of my audience are machine learning practitioners and researchers and things like that.
Yeah.
I wanted to ask specifically, what advantages might they gain from a realized quantum computer?
So that's another great question. It's great because, we don't really know the answer too well yet. This is an extremely active research area right now. And if you interview me 5 years from now, I am optimistic that we'll know more. Okay. But
we have HHL, right?
Yeah, that's right. But, I can tell you, so this has been a very hot area within the last decade, quantum machine learning. So, a lot of it is based off of a breakthrough result from a decade ago called the HHL algorithm by Harrow, Hasidim, and Lloyd. Okay, and this is a quantum algorithm that is sometimes billed as, being able to solve a system of linear equations exponentially faster than you could solve it classically. But there's a large number of caveats. The main caveat is that with this algorithm, so, you could imagine, I want to solve a linear system like AX equals B, where A is say an n by n matrix, right? I could imagine that A and B are stored in one of these quantum memories. I have to be able to access them coherently with a quantum computer. Then, I need some various technical conditions, on my matrix for this to work. But then the main caveat is that, after I've solved my system, meaning I've gotten out X, the solution, A inverse times B, X is not actually written anywhere in a memory where I can read it. X is just implicitly there as a vector of these quantum mechanical amplitudes. So I have a quantum state where the amplitudes encode my solution vector. At this point, the quantum algorithm person kind of shrugs their shoulders and says, okay, well, now it's your problem to design a way to measure that state that tells you something useful about your machine learning problem. It's quite plausible that there are situations where that can be done, where we could actually figure out a way to measure this superposition that gives you some useful statistical information about your solution. And furthermore, where getting that same information classically would be hard. That's kind of the question. That's what I think of as the active research area. So a lot of these quantum machine learning algorithms have a similar character as this HHL algorithm. Quantum mechanics is all about, at the mathematical level, it's all about doing linear algebra on very high dimensional vector spaces, right, extremely quickly. And a lot of machine learning is also about that. Right. So, so it's not surprising that a lot of machine learning tasks like support vector machines, like k-means classification, estimating, Betty numbers in topological data analysis, various other things in machine learning, would map pretty naturally onto a quantum process. Okay. But the issue is that when you do this mapping, often like you get an algorithm that sort of acts on an input that is itself a quantum state and then produces an output that is also a quantum state. Right. And okay, well, in order to, for it to be useful to us, well, we need to be able to start with classical data, and process it and then, make a measurement and get a classical output, and in such a way that we're outperforming a classical computer. It remains sort of an active research topic to figure out, to what extent can we take these quantum machine learning algorithms that often are just acting on quantum data and just go the full distance and turn them into a quantum algorithm that's actually useful in solving a classical machine learning problem faster than we could solve it classically.
Yeah.
So there are some proposals for how to do that. I would say that there is nothing yet that is sort of as decisive or striking as, say, Shor's factoring algorithm was in the 90s, right?
Mm-hmm.
But there are some candidates, and in particular, there was some very exciting work just a year or two ago by Jordan Karanidis and Anupam Prakash, which gave a quantum algorithm for generating recommendations in a recommendation system. So like if you're Amazon or you're Netflix, you have all this partial data about like which users liked or disliked which products. In this area, you typically make an assumption that there's like a matrix where users are the rows and products are the columns, and and how much the user likes the item is the entry. And you assume that this matrix can be approximated by a matrix of low rank. So there, so that like, your data is actually like explained by something of sort of much, much lower dimension. And then under that assumption, we can say for a given user, fill in the missing entries of the matrix. That is, generate more products that this user is likely to want to buy. And this is how these recommendation engines actually work. So what Karanidis and Prakash did is that they gave a quantum algorithm that if your user data is stored in one of these quantum memories that we were talking about, that's accessible by, making queries in superposition, then their algorithm would only have to make like a logarithmic number of queries to the data in order to, not to complete the whole matrix. It doesn't do that. All their algorithm does is it generates random recommendations for a given user that user is likely to like. For a recommendation engine, that's all you need anyway. Right? That's all you wanted. So they gave a quantum algorithm to do that, super efficiently, making very few queries to the data, whereas any known classical algorithm for the same problem seems to require a much larger number of queries. That actually hasn't been proven yet. No one has rigorously ruled out that there could be a classical algorithm for that limited task, that would also make very few queries. But, unlike P not equal to NP or P not equal to BQP or whatever, this is something that we can actually have hope to prove in our current state of knowledge, that just prove that, a classical algorithm will have to look at a large fraction of the memory in order to, say, generate good recommendations. And, this is actually something that I and my students have been thinking about trying to do. This is the kind of result that I'm hoping for, in the next 5 years or so that I feel will really clarify the situation with quantum machine learning algorithms. For many of these algorithms, like we know that, we would, to do something useful with them, we would need not only a quantum computer, but also a quantum RAM, quantum memory. Okay, but once you've got this quantum memory, then, you could hope to do at least some special things very, very quickly with a quantum computer, where classically we could just hope to prove outright that to do those same things would require, accessing a large fraction of the whole memory. There is sort of a much, much larger range of machine learning applications where a quantum computer can probably give you, if not an exponential advantage, at least a square root type of advantage, right? So I alluded to this before, but, so besides Shor's factoring algorithm, maybe the second most famous quantum algorithm is called Grover's algorithm. What Grover's algorithm does is that it searches sort of any list of n items in only about the square root of n steps. So that list could be stored in an actual memory somewhere, if it's a quantum memory, or it could be just the possible solutions to an NP-complete problem. But just anytime I have a whole list of possible items and I can quickly check whether any given item is correct, and I want to find an item that is correct, that meets my requirements, so I'm just looking for a needle in a haystack. Grover's algorithm lets me do that using a number of steps that's only like the square root of the number of pieces of hay. Right. So, so I get a quadratic advantage over what I could do classically. Okay. So that's not an exponential advantage like what, we think Shor's algorithm gives you. Okay. But it applies to a much, much wider range of problems, like anything involving search to a first approximation. So Grover's algorithm, I expect to be useful for lots and lots of things in machine learning, to give you these quadratic speedups. What I was talking about before was, okay, if you want an exponential speed up, then that's likely to be for more special problems. It's likely to be for problems, that would also require having a quantum RAM. But for some such problems, like for these recommendation systems thing, possibly for other tasks that are relevant in machine learning, you might be able to hope for an exponential speed up.
So let's say someone is an engineer, a highly ranked one at one of these, big tech companies, Netflix, Google, whatever.
Yes.
They've got a little bit of leeway to take on some moonshot projects, if you will.
Yeah.
And, at a place like that, a small incremental, like a 1% improvement on something can be millions of dollars. So it's definitely worth it.
Right.
At what point should they be looking into quantum as a possibility?
Well, I think people have sort of voted with their feet to answer this question. Google actually has a large quantum computing research group right now, one of the biggest. One of the leaders now in the effort to build superconducting quantum computers right now with about 50 qubits. So Google obviously decided that this is something that they want to have a group looking at, right, and sort of not be surprised about it. Netflix, I don't think that they've, I'm not aware that they've been involved, but, IBM has a big group doing quantum computing. Microsoft has a big group doing quantum computing. I know from my own experience that, there are many, many other companies and entities in Silicon Valley, for example, that are interested in this, that, want to just, learn about it, be aware of it. Right now, the devices are not there yet. Okay, we haven't gotten into this, right? But, there's this one company, D-Wave in Vancouver that sells 2,000 qubit devices. They've actually sold a few of them. They've gotten a lot of publicity and been very successful in raising funds. I think, partly because people wanted to do something right now with a quantum computer, and they were the only ones saying, well, yeah, we have a device right now that, that you can use. The problem with that is that the qubits, as far as we can tell, are not nearly good enough to actually do anything faster than you could do it with a classical computer. People ask, like, well, is it really a quantum computer or isn't it? Right? And I like to answer that by asking them, well, is a dirty bomb a nuclear weapon? Right? It's like, it's a computer. It computes something. It can solve some optimization problems. There are some quantum tunneling effects that are going on in the device, but the quantum effects that are there do not seem to be sort of nearly good enough or nearly well guarded enough against this decoherence to actually see a speed up. If you don't care about, actually getting an advantage, then there are people who are, already sort of taking various problems and doing them on the D-Wave device, just so that they can tell their mom that they did it with a quantum computer or whatever, right?
Yep.
But in terms of actually getting a speed up, my point of view has been, well, let's just first prove as clearly as possible that we can get a speed up for something. which doesn't have to be something useful. And that's this goal that's been saddled with the unfortunate name of quantum supremacy.
Mm-hmm.
Okay. But let's achieve this milestone of quantum supremacy, which, hopefully is coming within the next year or so. And then after that, we'll be in a better position to think about, what can we do that's useful? Where again, I'm pretty sure that the first useful applications are going to have to do with simulating quantum mechanics itself. Okay. And then after that, we can start thinking about, well, what can we do that is, useful for machine learning, for example. A lot of those applications, the trouble with them, as I mentioned, is that they're going to require not only a quantum computer, but also this quantum RAM, this quantum memory, right? Which is a whole separate problem to build that, and one that, almost no one has been thinking about yet. But if we have this large amount of data that's quantumly accessible in a memory, then we can start thinking about a lot of these machine learning applications on a super optimistic time frame. Maybe this is something that people could start doing within a decade or so. If we're worried about what's going to be relevant to industry in the next few years, look at classical stuff. People keep trying to find something that they can get from quantum, even without the hardware being there. Like, oh, well, maybe we can just use quantum analogies for classical machine learning or something. But, I would just say, just try to solve your classical problem by, whatever means is the best suited for that. Until the hardware is there, which, maybe, a decade from now or something. But in the meantime, one could certainly sort of acquaint oneself with what has been done in the theory of quantum machine learning algorithms. I wrote a little survey about this in Nature Physics, which was called Quantum Machine Learning, Read the Fine Print. There's another survey article in Science magazine, I think by Ashley Montanaro, Quantum Machine Learning. It's in Nature magazine, their supplement on quantum software, and it's by Jacob Baiamonte, Peter Wittek, Nicola Pancotti, Patrick Rebentrost, and Nathan Wiebe. Okay. So there are some surveys that have been written that, that explain both, the algorithms and just as importantly, sort of the caveats, all the conditions that would have to be met before any of these things, could actually give you an exponential speed up for a practical problem, right? And I think those are very important to understand as well.
Absolutely. I'll have links to those in the show notes.
Okay.
And also highly recommend people check out your book, Quantum Computing Since Democritus.
Thanks.
I really enjoyed it deeply, and I mean that from the heart. I've been through it 2 or 3 times now,
wow.
And I get something on every read.
All right. Well, thanks a lot.
Yeah. Well, Scott, thank you so much for taking the time to come on the show and share all of your expertise.
Of course. Thanks for having me.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.